Welcome to the course. This course is an introduction to the field of reinforcement learning and how to use OpenAI's software. This course is designed for those new to the field of reinforcement learning and machine learning. This course is also geared to those with a general interest in reinforcement learning and AI who wish to explore its applications in the professional and research fields. Minimum prior knowledge and experience is required. A basic understanding of Linux, Bash terminals, mathematics, Python, NumPy, Jupyter Notebooks, and TensorFlow will be very useful, but not required. You also will not need a high-end computer or GPU to run any of the code used in this course. In this course, you will learn to manage and install software for machine and reinforcement learning. We will use the popular Python package, Anaconda, so that we do not have any issues with package dependencies. We will go over the core concepts and terminology involved with reinforcement learning and how OpenAI's software is built upon these concepts. You will learn how to determine if something is best solved with reinforcement learning, and many applications outside of playing games where reinforcement learning is useful. When doing machine learning programming and research, there is some software that I would consider the standard that many others use. The most popular and easy to use operating system would be, in my opinion, Ubuntu 16.04. You can also use the previous LTS version, 14.04, but some additional packages are required for some software to work. Mac OS can work as well, but if you plan on using a GPU for some of your programming, Macs are very limited. The popular machine learning library, TensorFlow, no longer provides GPU support for Macs. One solution to this problem is you can use GPU cloud computing, such as Google Cloud. Windows 10 supports many GPU applications, but a lot of software, including OpenAI's GEM, is not supported. Python 3.5 is probably the programming language of choice for most machine learning applications. Most machine learning software is designed to work with Python as a package. You can use the standard Python installation along with pip to manage these additional packages, but I highly recommend that you use Anaconda instead. Anaconda is powered by Python, but comes with the most popular Python packages pre-installed. It manages all package versions to ensure that none will conflict with each other, and optimizes all packages for peak performance. Anaconda also makes installing difficult packages such as OpenCV extremely simple using their built-in installer, Conda. Anaconda is also used by OpenAI for research. There is a step-by-step guide for installing Anaconda and all the other software for this course in the working file installation.txt. If you have a modern NVIDIA GPU or plan on using TensorFlow on the Google Cloud, I highly recommend you build TensorFlow from source. In the working file installation.txt, there is a link to a tutorial on my GitHub, which has frequently updated in-depth instructions for building TensorFlow from sources and instructions for installing all software related to this course. When it comes to software, I almost never recommend using the latest versions unless you have a real good reason to. For example, the latest version of Python is 3.6, but I find 3.5 more reliable. As well, the latest Ubuntu is 17.04, but I highly recommend 16.04. This concludes the basics of what software to use for machine learning. So before we start installing some software, it's best to learn how to set up an Anaconda environment. An environment creates an isolated area for you to install all your Python packages. This is important because newer versions of software are frequently being released in machine learning, and these newer versions may not be compatible with code you wrote for older versions. TensorFlow is especially bad for this sometimes, but seems to be getting better. Environments are also helpful if you accidentally install a package incorrectly. You can then easily delete that environment and create a new one without affecting your Ubuntu installation. A general practice is to create a new environment for different styles of projects you may be working on. Assuming you already have Anaconda installed, let's get started by opening a terminal. We can create an environment by typing conda create -n. We then choose a name for this environment. For the Python version, we'll use 3.5, and then by putting Anaconda at the end of this will install all the popular Anaconda packages. Now I've already created this environment, but once an environment is created, we can activate it by typing source activate the name of the environment. You will then see the name of the environment appear in parentheses in your terminal. You want to make sure this environment is activated before installing any packages. Installing most packages will be done with the Conda Package Manager, but it is very helpful to install Python's standard package manager, pip. for some packages that Conda cannot install. We can install pip by simply typing conda install pip. You can see here that we already have the latest version of pip installed. A general rule to follow when installing a package is to use conda first, and if that package is not available through conda, then use pip. Almost all of OpenAI's software is installed using pip. An important thing to remember is once an environment is activated, you do not need super user access, or sudo, to install packages. Many tutorials call for you to use sudo when installing a Python package, but this is only necessary when working outside of an environment. The instructions for setting up a Conda environment for this course can be found in the working file environments.txt. So that is how you can install and manage packages in an Anaconda environment. Installing OpenAI's Gym is fairly straightforward. The basic instructions can be found in the working file installation.txt. Installing TensorFlow is required for some aspects of this course, and if you have a modern NVIDIA GPU or plan on using TensorFlow on Google Cloud, I highly recommend you install TensorFlow from source. In the working file installation.txt, there is a link to a tutorial on my GitHub which will walk you through how to install TensorFlow from source and how to install the rest of the software that will be used in this course. So getting started, we want to activate our environment in our terminal. We can install TensorFlow using pip. You can see I already have TensorFlow installed. To install Gym, we will need the version control software, Git. We can install that using sudo apt-get install git. You can see I have Git installed as well. We can find the address to the Gym repository on their GitHub. And we can copy this. We can then change into our root directory and clone Gym. You can copy and paste by hitting Ctrl-Shift-V. We then change into the Gym directory. Once we're in the Gym directory, we can install it using pip. We should now have Gym installed. If you would like to test to make sure Gym is installed correctly, we can open Python and import the package. We have now successfully installed OpenAI's Gym. So, what is reinforcement learning? Reinforcement learning is a branch of machine learning loosely inspired by behavioral psychology. Reinforcement learning is very different than the other two branches of machine learning, supervised and unsupervised learning. Reinforcement learning involves an agent, or algorithm, or decision maker that interacts with an environment. The agent learns optimal actions in order to maximize a total reward defined by that environment. Some popular examples of reinforcement learning are DeepMind's achievement in training an agent to play Atari games, and AlphaGo, an agent that has defeated world champion Go players. It's important to remember that reinforcement learning is a science of decision making, and that it's not just for games, though it works very well in a games environment. Reinforcement learning can solve an array of different types of problems, and it can do so thinking outside the box of normal human decision making. A popular example of this thinking outside the box would be AlphaGo creating a new, unconventional style of playing Go that professional Go players are now learning and adapting their playing styles to. This is extremely impressive given that Go is one of the oldest board games dating back 2,500 years. Reinforcement learning also has large potential for helping pave the road to machine intelligence. Facebook's AI director, Jan LeCun, referred to reinforcement learning being the cherry on the top of the cake of machine prediction, the icing of that cake being supervised learning, and the bulk, the cake, being unsupervised learning. Reinforcement learning can also be used for many robotics and motor control applications, including self-driving cars. It is also very helpful for things such as inventory and sales management, where maximizing efficiency is key. It is my belief that reinforcement learning was also used by DeepMind to maximize Google's servers' energy and cooling efficiency, leading to a reduced power cost of 40%. There is a text file with links to popular and interesting reinforcement learning applications and the working file examples.txt. OpenAI is a nonprofit with the mission to build safe AGI, which stands for Artificial General Intelligence. OpenAI is working on advancing machine learning research. They are also working on general-purpose robotics and publish open-source software tools such as Gym and Universe. These tools are designed to help machine learning developers test reinforcement learning algorithms. This software also acts as a stable benchmark for people to compare the performance of their agents. There are a couple concepts in terminology and reinforcement learning that are crucial to understand before trying to solve your own reinforcement learning problems, or those in GEM. These terms and concepts are generally universal across the reinforcement learning community. First is the agent. The agent is your algorithm and is what decides which actions to take. The agent normally has some defined goal and can monitor or sense aspects of the environment. The environment is anything the agent can interact with. It is important to remember that it is easy to confuse environment and agent. For example, in a maze, the unit that moves is part of the environment, and it is the agent's actions that result in the unit moving within this environment. Another example would be a cart trying to balance a pole. The cart is part of the environment, and the variables such as cart position, cart velocity, pole angle, and pole angular velocity are things that can change in the environment as a result from the agent's actions. The state is what the environment sends to the agent to be interpreted. In the example of a simple maze, the easiest way to represent the state is to assign a number to each possible state. For example, the maze below has 20 possible squares that the red square can navigate. And if we were to number the squares from left to right, starting from S, we would consider the red square being in state 11. In regards to an Atari game environment, the state is represented by the values of every RGB pixel. The current state does not always involve the entire environment and is limited by what the agent can sense. In the case of a self-driving car, the state is limited to what all the car's sensors can detect, not the entire world. The state can also be reinterpreted by the agent as well. One example of this is in an entire environment, one can convert the state to grayscale to lessen the possible state space, allowing the agent to learn easier. The action is what the agent decides to do in a current state in an attempt to change the environment to maximize reward. The amount of possible actions are limited by the environment. In the case of a simple maze, the possible actions are to move up, down, left, or right. Or in the case of an Atari game breakout, the possible actions are left, right, fire, or the action of doing nothing at all. As an action is taken and the environment changes, we consider the time step to advance by 1. This time step acts as a counter for the environment. The reward is what helps define the goal in a reinforcement learning problem. In each time step, the environment returns a reward to the agent, and it's the agent's goal to maximize this reward. Rewards can be positive or negative, and can either reinforce or penalize certain actions or policies of the agent. For hopefully obvious reasons, it is essential that the agent cannot modify the reward system of the environment. Taking all these concepts together, we can create the standard reinforcement learning loop. The agent is given its current state, and using the algorithm, it decides an action to take. That action then affects the environment, in which the environment returns a new future state and reward. The agent then interprets this new state and reward it received from the previous action, then decides what to do next. So let's begin with exploring the basics of GEM. First, let's activate our Anaconda environment. I prefer using the IPython shell because it's more interactive and allows me to explore the GEM API easier. We can start with importing GEM. Now there are a lot of functions built into GEM that are essential for creating an agent that can solve multiple environments, rather than just specializing on one. We will explore these functions in different environments. For our first environment, we will use the toy text example, taxi. We can create an environment using the gem.make command. To initialize the environment and get our initial state, we must first reset the environment using env.reset. You will notice that resetting the taxi environment will return an integer. This number is our initial state. The taxi environment has a total of 500 different possible states. Terminal states are when the environment ends and do not count as a possible state space. To determine the total amount of possible states for this environment, we can use m.observation_space. This confirms there is 500 different possible states. So this state integer is how the agent will understand the environment, but let's visualize the environment so it makes more sense to us. You can visualize the environment using m.render. In this environment, the yellow square represents the taxi. The lines represent walls, the blue letter is the pickup location, and the purple letter is the drop-off location. The taxi will turn green when the passenger is aboard. The goal of this environment is to as quickly as possible move towards the passenger, pick them up, and drop them off at the drop-off location. Next, we can determine the total available actions that the agent can choose from. We can do this using env.actionSpace. This shows us that there is a total of 6 actions available to the agent. Jim will not always tell you what these actions mean, but in this example, the 6 actions are move down, up, right, left, pick up, and drop off. It is not important to the agent exactly what these actions do. The only thing the agent is concerned about is the reward it receives for doing these actions. Another very important part of using Jim in developing your own agents is being able to take completely random actions. Random actions help in the learning process and also act as a great baseline for quantifiable improvement. Rather than programming our own action generator, we can choose a random action using m.actionSpaceSample. This will return a random integer between 0 and 5 for our action. Now for learning's sake, let's override the current state using m.s and render. Let's see what happens when we move up. You will notice that this action returns 4 variables from the environment. These 4 variables are the new state, reward, a boolean stating if the environment is terminated, and extra debugging info that you normally will not use. Your agent should never use the debugging info, as it's considered a form of cheating. A common way to define all these variables is as follows. This will cause the agent to move up again. Do you think the state space has changed? No, it hasn't, because we hit a wall. What if we decide to pick up a passenger? Of course the state has changed. We're in the same position, but now the passenger is inside the taxi. Not every environment is as simple as taxi, so let's move on to a more complex Atari environment and explore the same functions. And let's define our initial state. You will notice that the state is a 210 by 160 by 3 tensor, which is the RGB values for each pixel. Or simply put, these are the raw pixels. You can also get this shape using the observation space command. You can also get the max of the observation space by adding .high. This would be an entirely white screen. You can also get the min by adding .low. This would be a completely black screen. So in a sense, every Atari game has to exist within this range. The high-low functions are a lot more functional environments such as mountain car. As before, we can look at the number of possible actions using action space. And for the Atari environments, OpenAI was very helpful and added a description of the possible actions which you can get using m.getActionMeanings. This shows that the 4 actions are do nothing, fire, right, and left. And finally, we can render the environment using m.render. This concludes the basics of using the Jim API. If you'd like to further explore all the available environments in Jim, the best place to do so is on their website, under the Environments tab. Here you can find all the available environments. If you would like a list of all the environments in the terminal, you can do so with the following command. Here's a list of all the available environments. Another fun feature is you can actually play all the Atari games using the following command. The play script will default to Montezuma Revenge, but if you'd like to try a different game, you just need to edit the PI file. You would insert the game you want to play in this line here. So what is a Markov decision process, and how does it relate to reinforcement learning? A Markov decision process, or MDP for short, is a mathematical framework for modeling decision-making and can be used to represent any reinforcement learning problem. For reinforcement learning, MDPs are a way to model our environment. MDPs use time steps and map a current state at each time step. The agent may choose any action that is available in this state at a given time step. This is a way of mapping the relationship between taking an action in a current state and the new reward and new state. Here's a simple example. In this MDP, we start in state 0, and we have the options of moving left or right. Let's see how it relates to the reinforcement learning loop. Looking at our variables below, the initial time step is 0. Our current state is represented by S, which is 0, and G represents our total reward, which is 0 as well. A represents the action taken at a given time step. Our agent will decide to go left. Our agent performs the action, and our environment responds with a new reward and state. If the current state is terminal, the time step will not advance. The time step does not advance till after this dotted line seen above in the reinforcement learning loop. Starting over, how will things change if we always go right? Let's step through the process. First, the agent takes an action, and the environment returns a new state and reward. The time step advances, and our current state and reward gets updated. The agent then decides to go right again. The environment changes and returns a new reward and state. Then the time step updates, and we can do this complete loop once again with another time step update. Then the environment terminates with a reward of 3, and we do not update the time step. So how do we solve an MDP? And again, how does this relate to reinforcement learning? A common solution for solving an MDP is to use a Q-learning iterative update. If we know exactly how the model looks, we can easily solve this problem other ways. But let's pretend we do not know all the possible rewards for this MDP. Q-learning is a way of determining the action value of taking an action in a given state. This action value is also referred to as the Q value. The action value can loosely be defined as how good it is for the agent to take an action while in a given state. In order to determine an optimal policy for the environment, we have to try and determine the value of every state and action pair in the environment. These action values allow the agent to choose which action is best to take in a given state. Action values need to be estimated from experience over multiple episodes of the same MDP. It is not until we try all possible actions and states over multiple episodes that we can determine a converged action values. Values update recursively in a sense, given that the values are updated backwards starting from terminal states. So let's take a look at the previous MDP example. We start with an action value, or Q table, of all the possible states and actions set to 0. We can then take an action and update the table using the formula below. If the agent decides to go left, it will update the value for Q0L from 0 to 1. Breaking down the formula, we have our old value for Q0L, which is 0. For learning rate, we will use 1. This defines how quickly we will update action values. Our reward after taking the action left will be +1. For discount, we will use 1. We can ignore what discount does for now. We then use the maximum action value of the state we transitioned to. Since the state is terminal, it does not have a value. And we finish by subtracting the old value for Q0L, which was 0. If we were to start another episode and decide to go right, what do you think the value of right in state 0 would be? It would of course be -1. Now you might think that this is a problem, and that our agent may just always decide to go left and not discover that going all the way right is the optimal solution. This situation deals with the problem of exploration versus exploitation. The solution to deal with the dilemma of exploration versus exploitation is that we should have the agent also try random actions, rather than just what it thinks is best given what it knows. This allows us to explore the environment and update our action values. Let's pretend that from state 1 we continued all the way to state 3 and then terminal. We could then calculate the value of going right while in state 3 to be 3. Let's update our values backwards. The value for going right in state 2 can be updated to 3, and the same for going right in state 1. Then using our previous value of -1 for going right in state 0, we can update the value for going right in state 0 to be 2. Now, based upon our action values, we can determine the best policy is to always go right. Of course, in an actual environment, we would not be able to move backwards. But given enough episodes and enough exploration, you would converge on similar values. And that's how we would solve an MDP using Q-learning. So when should you use reinforcement learning to solve a problem? First of all, you will not be able to solve a problem using reinforcement learning if it cannot fit into the context of an MDP. I will apply this context to 2 very different examples: a simple robot that has to balance upright, and a hot dog stand trying to decide how many hot dogs to have pre-cooked and prepared to sell. Your environment will have to have some sort of termination point. This could be when the robot falls over, or the end of the sales day for the hot dog stand. Your environment will also need some sort of reward. For the robot, this reward could be how long the robot manages to stay upright. And for the hot dog stand, this could be a positive reward for when someone orders a hot dog and one is cooked ready to go, and a negative reward if someone orders a hot dog and one isn't cooked. Your state will also have to be represented mathematically in some way. Let's imagine our robot is very simple and is a fixed motor with a pole attached to it. We could represent its state as the current angle of the pole. For the hot dog stand, this could simply be how many cooked hot dogs you currently have. We can of course add more ways to represent the state, but the higher and more varying the possible state space, the more difficult it will be to solve the problem. Reinforcement learning is also more practical in some situations where you simply do not have a lot of data. Reinforcement learning is always in production and can learn from constant new data. There is, of course, some situations where other types of machine learning are more practical. If you had years of data of hot dog sales, it would be better to use a supervised learning approach to determine the optimal amount of cooked hot dogs needed. Of course, if you wanted to do image detection whether or not something is a hot dog, a supervised machine learning approach would be best as well. If defining your own environment, the reward structure is crucial to developing an agent that can learn. If you want an agent to solve an environment as soon as possible, often the best way to have the agent learn is to have a -1 reward for each time step and a large positive reward when the environment is solved. In some examples, such as balancing a poll, the ultimate goal is to have the agent continuously perform a task, and in this case, the best structure is to have a positive reward for each advanced time step, with no negative reward for falling over and terminating. So let's look at methods on how to solve the basic taxi environment. You can find this IPython notebook in the working file solvingtaxi.ipynb. We start by importing NumPy and Gem, define our environment, and reset it. We can also print out our current state and render the environment. In Taxi, the possible actions are down, up, right, left, pick up, and drop off. We can define the number of possible states and the number of possible actions given the following. A great way to define a baseline for improvement is to try a completely random policy. The taxi environment will normally define done as true after 200 time steps, so we will create a loop that won't terminate until the environment returns a reward of 20. You may luck out and solve the environment quickly, but on average, it's going to take about 2,000 time steps to solve this environment behaving completely randomly. So behaving randomly didn't perform that well. Let's use a value iteration update and see how that updates our Q values after one episode. We'll define the number of episodes just to be 1. We will create a Q table for storing all possible state action pairs. This will be an array of 500 possible states by 6 possible actions. We will also keep a history of all the Q value updates for each time step using a 3D array QHist. The first variable in the QHist is the state index. The second is the action index, and the third is the time step index. This time, we will use a smaller learning rate so that our algorithm updates our action values slower. We will also use the variable g to monitor our total reward for each episode. We can now run the algorithm for one episode until the agent receives a reward of +20. So now that the agent has solved the environment for just one episode, let's look at how the Q values updated for each time step. So looking at all the action values for the initial state of 208, we see that the agent chose the action 0, go down, and received a reward of -1. When the agent was making its decision using the argmax, the action values for each possible action was 0, so it chose the first index. Since our learning rate is 0.618, it will update the action value to -0.618. Let's look at the final step. You can tell looking at the Q history that there was a total of 511 time steps. Since that 511 includes the index of 0, there was a total of 510 steps. Looking at the final step in state 16, you can see that the agent had previously tried all actions starting at index 0. It tried all the movements and received a reward of -1. It tried picking up and received a reward of -10. And then finally, it dropped off and received a reward of +20. Now after just one episode, the agent knows when in state 16, the optimal action is to drop off the passenger. But how about the state before the final state at 16, at the total time steps -1? Do you think the agent would know the best possible action? Of course it wouldn't. When currently in this state, it has no estimate of a potential good future reward. The agent would have to complete another episode and revisit the second last state in order to update its estimates of future rewards learned from the previous episode. The agent will know, though, what actions it thinks are the worst. So let's run this algorithm over multiple episodes. We can see that after 200 episodes, the agent begins to learn an optimal policy. And as we progress into the future, our total average reward also increases. Now that we've learned the optimal policy, we have no need to train our agent anymore, and we can also evaluate our learned policy. You can see that the agent learns to solve the environment as quickly as possible. So let's try and take the knowledge from solving the taxi environment and try and solve the frozen lake environment. You can find this IPython notebook in the working file frozenlake.ipynb. As before, we will start by importing NumPy and Gym, defining our environment, defining the number of possible states and actions, and render our environment to take a look at it. Frozen Lake is a rather simple environment and only consists of 16 possible states and 4 possible actions. The goal is to get to the end labeled as G without stepping in any of the holes represented by H. The environment only gives a +1 reward for getting to the goal and a 0 reward for everything else. The environment will terminate if you fall in a hole. The main problem that makes this environment tricky is your state transition probability is unknown. Before, with Taxi, we were always 100% certain the agent's actions were taken. But with frozen ice, the environment is slippy, so the environment may cause you to go somewhere you did not expect to go. The movement direction of the agent is uncertain and only partially depends on the chosen direction. This unknown state transition probability will make it very hard for the agent to learn, because it has a hard time determining the actions and state transitions that it actually wanted to do versus the state transitions the environment returns. Let's try behaving completely random and see how that does. Always choosing a random action will eventually get to the goal, but with a very low success rate. How about our previous Q-learning algorithm we used to solve Taxi? This algorithm will not work at all, because every state transition, except for getting to the goal point, will give a reward of 0. Our agent will just continuously try action 0 and not update any of the Q values. If you remember from the Taxi environment, each movement state transition gave a reward of -1, and this alone resulted in the agent exploring new actions with higher Q values. One solution to this problem is we can create an epsilon greedy policy that will choose a random action at a given epsilon percentage. We will set our epsilon to 0.5. You can see here under this while loop that instead of choosing an action based upon the argmax of our Q values, we will instead, with an epsilon percentage chance, choose a random action. numpy.random.rand will of course return a random number between 0 and 1. If this random number is greater than epsilon, we will take the argmax. If this random number is less than epsilon, we will do a random action. Let's see how this performs. This still only gives us about a 3% success rate, not very impressive. In order to achieve better results, we're going to have to add discounting as well. So what is reward discounting, and when do we want to use it? Discounting allows us to determine the present value of estimated future rewards. Think of it simply as, would you prefer $20 now versus $100 sometime in the next 3 years? Most of us would probably just take the $20. We represent our reward discounting by the symbol gamma. For gamma, we'll use a value between 0 and 1. If gamma equals 0, your agent will be myopic, or simply put, short-sighted. As gamma approaches 1, the agent will become more farsighted, giving potential future rewards more merit. Before, we were always using a discount of 1, but now we will want to use discounting so our agent gives slightly more merit to its immediate rewards. So let's look at the previous MDP. Looking at the formula for our total discounted reward, we can see that the reward will be exponentially discounted each time step. If we were to choose the action left from state 0, we simply would receive an undiscounted reward of 1. Let's pretend we know our model. Let's calculate the expected 0.85 discounted return for always moving right while in state 0. This would give a return of 0.84, and if we were to use a discounting rate of 0.85, our agent would always choose to go left from state 0. But we almost never know a complete environment. So let's look backwards from solving this environment using our value iteration update and our always go right policy. At the point of termination, we no longer have any estimated future rewards, so no discounting will apply. On our second episode, transitioning from state 2 to 3, we will discount the expected reward of 3 by 0.85. On our third episode, we will discount that estimated future reward again. And finally, adding a -1 reward to our discounted total reward. Here, you can see the complete steps involved with discounting an expected reward after many episodes. Most of the time, a discount of 0.85 is too drastic, and in practice, the most common used discount rates are 0.95 and 0.99. In this simple MDP, these two discount rates will result in an agent going right every time. So let's go through the advanced steps involved with solving the frozen ice environment. In order to solve this environment by OpenAI standards, we must receive an average reward of 0.78 over 100 consecutive episodes. We'll use the same learning rate alpha as before, but this time we'll use reward discounting and a decaying epsilon rate. Earlier, we had used a fixed epsilon rate of 0.5, and this caused the agent to 50% of the time choose a random action. This allowed the agent to explore lots of possibilities, but did not consistently exploit the best actions once they were learned. So instead, we'll start with an epsilon of 1 and decay it by 0.001 or 10 to the power of -3 each time a random action is chosen. Eventually, after so many random actions, the agent will only choose the argmax. This is a great example of an on-policy agent because it's constantly updating how it behaves after each step. On-policy is where your training and evaluation are happening at the same time. An example of an off-policy agent would be an agent that behaves randomly 100% of the time to learn a policy that will later be used in evaluation. So let's see how this agent does. The agent did pretty good that time around. Let's see how it does again. Wow, that's a lot worse than before. You may have noticed that this agent was not very dependable. The reason this algorithm is so unpredictable is because it's mainly dependent on how luckily it chose the right random action. This agent is more dependent on a random action than it is learning an actual policy. In order to solve this environment, we needed to find a more appropriate epsilon greedy policy. The best approach is to add random decaying noise to the argmax policy. Each time the agent takes its greedy action, we will add a random normal distribution number to all the Q values, and divide that by the episode number. This ensures as the episodes increase, the amount of random noise will decrease. As before, we will decay our epsilon as well, but at a much smaller rate. Much like any other machine learning problem, you need to discover and define optimal hyperparameters. We can create a function for our training process that will allow us to experiment with our hyperparameters. I found the best parameters were 0.8 for the learning rate, 0.95 for our gamma, and 0.1 for our epsilon. This seems to almost always solve the environment with an average of about 1,500 episodes. And there we have it. We solved the environment. We can also create a function to evaluate our policy to see its total average return, and finally, visualize the agent's performance. As you can see, the agent's actions may not make complete sense to us, but it's learned this policy from the environment to be the safest route possible to get to the goal. What is considered deep reinforcement learning, and how can it help us solve more complex environments? All deep reinforcement learning uses something called function approximation. Function approximation deals with generalization. A function approximation problem asks us to select a function among a well-defined class that closely matches a target function in a task-specific way. Often, in reinforcement learning, we are trying to define the set of classes and functions required to maximize reward based upon our input. Neural networks, support vector machines, pattern detection, logistic regression, tau coding, and many other supervised learning methods can all be used for function approximation. So when do we need a function approximator? Essentially, as soon as your state space involves floats rather than integers and is higher dimensional, you are probably going to need some sort of function approximation. Let's take mountain car for example. Our state is represented by two floats, the first one representing our current position and the second representing our velocity. We wouldn't want to make a Q value table for every 100th decimal place. Also, how could we create a single state out of the two variables? Just simply adding them certainly would not work. We need to use some sort of function approximator. There are many ways we could do this. We could feed our two inputs into a neural network and output a probability of taking a certain action. We could also take the raw pixel values and feed them through a deep neural network, possibly using convolutional layers. But we'll keep it simple at first and use a not widely known but very efficient model called tau coding. Think of it like this. You have a two-dimensional input space in which you have an infinite amount of possibilities. Imagine our environment returns a state of 2.3 and 2.7. To use tau coding, we'll have to decide how many tilings we'd like to use. For this example, I'll use a total of 6 tilings. We also have to decide how many tiles each tiling will have. For this example, I will use 49 tiles per tiling. So here we have tiling 1 with its 49 indices. We can see that tile 17 lays in the range of our state space. We will record this integer and continue by sliding the tiling and creating a new tiling. Here on tiling number 2, you can see tile 66 is activated. continued with 122 on tiling 3, 171, 221, and finally 270 on tiling number 6. We can now represent an area based upon the current state space by using 6 integers. The beauty and simplicity of tile coding is we can also represent state action pairs. Say we have 3 possible actions. The initial tile coding output can represent action 0, and then we simply multiply this number by 2 and 3 to get integers that represent that state action pair for actions 1 and 2. For every possible tile, we will also have an associated theta value, which we can use to calculate our Q values. Tile coding can also be used for higher dimensional problems as well, but often, some tweaking and value normalization is required. Policy gradient methods are probably the most popular for function approximation used in deep reinforcement learning. Policy gradient methods attempt to use gradient ascent to try and estimate which actions lead to a reward. Unlike Google's DeepQN network, these do not require the calculation of any Q values. It is simply trying to develop a policy that leads to rewards, rather than estimating the value of taking a particular action. Much like deep learning, policy gradient methods are very difficult and time-consuming to train. Once tweaked and trained properly, though, policy gradient methods have proven incredible results, especially in robotic simulations. Other types of popular policy gradient methods that incorporate a Q value are actor-critic methods and A3C methods. Policy gradient methods can, but do not always have to be a deep model. By deep, we mean more than one layer in a neural network. Policy gradient methods can be used to solve simple problems, such as mountain car. I find often that for most simple tasks, policy gradient methods need far too much tweaking and training time to justify use. In order to solve complex Atari games more efficiently without any pre-processing of the pixels, techniques such as convolutional neural networks are added to help better represent the pixels from a game. These methods require powerful GPUs and large amounts of training time. To help these deep networks learn more efficiently, new techniques and research comes out literally on a weekly basis. Techniques such as dropout, more efficient activation functions, learning rate decay, epsilon greedy methods, adding random noise are some of the few methods used to help train deep RL models. This includes a few of the popular methods for function approximation, including tile coding, policy gradient methods, and deep neural networks. So let's look at how we can solve the mountain car environment using tile coding. We start by defining our tile coding class, which will take in the number of tilings we'd like to use and the one-dimensional count of the tiles we'd like to use per tiling. We can discover the range in which our tile coder will operate using the observation high and low commands. The dimension of our tile coder will simply be the length of our possible state space. In this case, our dimensions are 2. With a tiles 1D of 18 and a number of tilings of 4, each tile will have 18 squared tilings, with a total of 1,296 tiles. Combining these 1,296 tiles with the 3 possible actions leaves us with a total of 3,888 tiles represented by n. We then have to define our feature mapper, getFeatures, that will take in our current state and return 4 integers, which represent the 4 tile indices for each tiling. It's important that our values never go below 0, because negative numbers will confuse our tile coder. The function for returning these tile indices as a list is a little complicated, but allows you to work with a higher dimensional space when needed. We then create the function getQ for assigning our Q values to the possible actions. The getQ function calls the getVal function, which will return the Q values from the state features. Lastly, we need to make a one-hot vector, which will be used for updating theta using our learning rate. We can then create our environment, create a tile coder, and initialize our theta randomly. I've made a custom learning rate that seems to adapt well to different environments. The nice thing about the mountain car environment is since we want to solve the environment as quickly as possible, the environment will return a -1 reward for each time step. This allows us to not need reward discounting, so we'll set gamma to 1. We start with our episode loop by setting our total episode reward g to 0 and resetting our environment. We then get our features from the tile coder and calculate our Q values. We then perform our state update. We then update our total reward, and we update the variable delta, which will be used for updating our theta. If the episode is finished, we update our theta and start the loop over again. If the episode is not finished, we get the Q values for the future state 2, update our delta to reflect predicted future rewards, and then update our theta and advance the time step. In order to consider this environment solved by OpenAI standards, you will need to get an average of negative 110 reward over 100 consecutive episodes. So let's see how quickly we can solve the environment. And there we have it. We've solved the environment. Let's look at the code required for solving the Atari game Pong. We'll be using a very simple policy gradient method that will be feeding our raw pixel values into a 2-layer, fully connected neural network. The nice thing about this example is it can be run on a simple laptop. It only takes about 1 full day to train. Also, once we've trained a model, we can visualize the neurons that help the agent take its actions. Starting with our variables, we'll create our environment and make a list of all episode states, rewards, and action history. Like before, G will represent our total episode reward. Our N input will be our pixel inputs. In order for TensorFlow to understand the pixels, we'll have to flatten the 80 by 80 vector into a 1 by 6400 vector. We will use 200 neurons in our hidden layer, and our output will have 3 possible actions for our output layer. We'll use the standard learning and decay rates for our TensorFlow optimizer. We start by randomly initializing our weights. These will be the core of how our agent will learn what actions to take while in a given state. We create a function for processing our raw pixels from a 210 by 160 by 3 tensor to an 80 by 80 grayscale image of only ones and zeros. We will crop out all unnecessary space and leave behind only the ball and paddles. This will help our agent learn much faster. We define a reward discounting function that will apply discounting to multiple sets of rewards, and define our feed-forward policy, which feeds our inputs through the neural network and returns an action probability for our 3 outputs. It's very important to understand what softmax does. This will take our numerical outputs and convert the numbers into a probability. With softmax, the sum of all the outputs will always be equal to 1. Placeholders are an essential part of TensorFlow, and as their names suggest, they act as boxes in which we can feed changing data into. In this case, X represents our pixel inputs. Y is a one-hot vector that represents our action, and EPR represents our rewards. We then define our loss function, which will subtract our action probabilities from our one-hot action vector. Essentially, we want to minimize our confusion and maximize our confidence in taking a certain action. For an optimizer, we'll use the atom optimizer. We finish off with functions for updating our weight values using TensorFlow's backpropagation. We then create our TensorFlow session and initialize all our variables. We can create a safer function, so if we want to stop and reload our model at any point, we can. You may have to create a models folder in the directory you run the Jupyter Notebook, depending on your write access. We can start running the game and training our model. I've set up some basic learning rate decay based upon the episode number. A crucial part for getting our agent to learn is developing intuition about motion and speed. This can be accomplished by subtracting the previous frame from the current frame. We will also store the state 1 as state 2 so that we can compare it to future states. Here's an example of the frame processing. Here, the game begins. You can tell the motion based upon the black trail of the white objects. Here, we will see the ball move towards the computer player. He then bounces it back. Continuing on, we feed our pixels into our neural network and get an action probability. We then choose an action randomly based upon our probabilities. This will help our agent take many random actions until it starts to develop more confidence in its actions. We then take an action and assign our new future state. We then record our state, action label, and reward history. If an episode is complete, we then feed our data into the neural network to be backpropagated. We then update our weights, reset our environment, and begin a new episode. As you can see here, I ran my model for just over 4,000 episodes and just started winning games with a high percentage. Let's see how our agent performs. It did pretty good that time. Let's try once more. Let's see it perform just one more time. It seems to be doing a really good job, but every now and then it kind of drops the ball. Let's look at the weights of our neural network to try and gather some intuition about how our agent is performing and choosing its actions. Our weights are pretty noisy, and rightly so given that we've played well over 100,000 games of Pong. You start to see some areas become highlighted that represent the motion of the ball and the paddle. Here, in this frame, you can tell the agent would be very confident in its action if the ball was traveling in its current path and if the opponent was at the bottom of the screen. Amazingly, each neuron acts as a transparency that it puts on top of our current state. If a pixel is highlighted in red square, the output for that individual weight neuron will increase. One thing that I found very fun was experimenting with different ideas and running the code for a day. One idea that I had was maybe if I remove the opponent's paddle, maybe my paddle would just learn how to hit the ball and not care about where the opponent was. Unfortunately, this did not work. I challenge you to try and achieve better results, possibly by normalizing our input data, adding a bias, or by processing our pixels better. If you have a modern GPU, you could also try using a convolutional neural network. If you would like to solve this environment and many other Atari environments using some of the latest techniques, check out the link in the working file universe-starter-agent.txt. This IPython notebook can be found in the working files labeled pong policygrad.ipynb.